Hi class, welcome to an example problem for Unit 9.1. Unit 9 is a bit different than the other units we've done so far in this class. We're learning about centroids and moments of inertia. And what a centroid is, kind of like the name implies, it's the center of a shape. It's the point where if you were to imagine you stick a pin right at the centroid, the shape would balance perfectly. Sometimes you'll hear things like center of gravity or center of mass. Centroid's basically the same thing. Um, so in this problem here, this is problem 9-63 in the 13th edition of the book. In the book, the diagram looks, let's see if I can, look something like this, where you kind of get these two C channels that are resting on top of each other. The C channels are the same shape, so I've redrawn it here. So here's our 1C channel. This length is 2 inches long, it's 10 inches tall, and again 2 inches long here at the bottom, and it's 0.5 inches thick. And the same dimensions for this C channel, except it's laying on its side. 10 inches long, 2 inches wide, 1.5 inches what sticks above here, 0.5 inch thickness all the way about. And what we're asked to find is to find the centroid of this combined shape, these two C channels. So how do we go about doing that? There's a lot of different ways that you can do this. This is kind of what you might call finding the centroid of a composite body. Right? It's really easy to find a centroid of a simple shape like a square, a rectangle, a circle, a triangle, but this is sort of a whole bunch of rectangles stuck together. So there's different ways that you could do this. The key equation we're going to use is that the centroid of a shape, so if we're looking for, we're going to do it both the x and the y centroid. So if we're looking at x, the equation in question is that the centroid in x, which we represent by this little bar, so x bar equals the summation of the area of our individual component shapes times the centroid of that individual shape, which we're going to represent with this little tilde, all divided by the summation of the area of our individual shapes. So this says if you have a bunch of different shapes that combine to form a bigger shape, more complex shape, you can find the centroid by just basically, this is, if you are familiar with other, like stats or things like this, is essentially a weighted average of the centroids of each of your individual shapes. So if we wanted, right, we could break this up a couple different ways. We could say, hey, maybe I'm going to look at this rectangle right here, and this rectangle, and this rectangle, and same on this shape, and find the area of each of those where the centroid is in x, and sum those up according to this weighted average. The way I'm going to do it is a way that will let me use a few less individual shapes. So what I'm going to do is I'm going to take the centroid of this big, I'm going to imagine, my blue pen is dying on me. I'm going to look at the C channel and say, I'm going to find the centroid of, what if it was this full larger rectangle? And then because it's the C channel isn't actually that big, I'm going to then subtract this slightly smaller rectangle that would fit inside the C portion of that. Hopefully that kind of makes sense. So we're gonna, and that way I can represent each C channel as just two rectangles instead of three. And the cool thing is that is a totally valid thing to do. So if we look at this big rectangle that we would have if there wasn't this cutout in the C channel, let's start with this lower guy. So what do we have? We have, first we're going to find the area of this big rectangle, which is 2 by 10. So we get 2 times 10, and its centroid in x of this big rectangle is the midway point for rectangle, so it's at 5 because it's 10 long. And now we need to subtract this cutout portion because it's not actually there. So we're going to say minus, and that cutout portion is 1.5 tall and 9 long, and its centroid is also at 5. And now we're going to do the same thing for this tall guy. So it is 2 times 10, and its centroid is conveniently also at 5. And then we're going to take this, we're going to subtract out this cutout piece here. So minus, and that is also, just like the other one, it's 1.5 times 9. Now its x-centroid is not right at 5, right? It's actually going to be like over here. It's offset a little bit. So it is actually, if we look at the math, if we do the math, it's at 5.25, right? It's offset by a quarter inch to the right. And now we have to divide all of that by the sum of the areas. Now in the denominator, in the same places where we add, we'll add. In the same places where we subtract the shape, we'll subtract the area. So we'll say 2 times 10 for the big rectangle minus 1.5 times 9 for this piece that isn't actually there, plus 2 times 10 minus 1.5 times 9. And if we do all that math, we end up getting that x bar equals 61.625 in the numerator, and in the denominator it's 13, which gets us 4.74 inches. So it is at 4.74 inches that we have our centroid in the x direction. Right, and that kind of makes sense, right? If it would be, the centroid would be right at 5 if we, these were the full blocks, but because this C channel is, it's, really you can kind of imagine its center of gravity, its centroid would be a little bit left of the center. So it makes sense that our centroid is going to be slightly off center and a little bit to the left. So we can do the same thing now for the y centroid. It's the same basic equation, the sum of the areas times the individual areas y centroid divided by the sum of the areas. And so same thing, we're going to start with this big guy. And so we have its area is 2 times 10, and because it's too high, its y bar, its y tilde is just 1. And now we need to subtract this cutout area. So it is just like before, the area is the same, 1.5 times 9, and its y bar, it is not at 1, it's shifted up by a quarter inch, right? Because it'll be the center of this guy, which is 7.5 plus the 0.5 offset here. So that gives us 1.25, and then plus, now we're looking at this big rectangle that we would have up there, 2 times 10 times, and its y bar is at 5.5, right? Because it would be, if you're just looking at this shape, it's 10 high, so the centroid would be 5 inches here, but then it's offset by 5 inches because it's sitting on top of this C channel there, so 5.5. And then minus the cutout area there, which is 1.5 times 9. And it is also going to have, it's going to have the same y bar, or y tilde 5.5. And then we just divide all that by the areas, which is going to be the exact same thing as before. So I'm just going to reuse, I know it's 13. Nothing's changed about the area. So what I end up getting is y bar equals 38.875 divided by 13, which is equal to 2.99 inches. So those are my answers. So hopefully that makes sense. Centroids of composite shapes are really nothing that complex. The most important thing is to just have good bookkeeping. Make sure you are very clear on what shape is what, how you're breaking it into pieces, and be really careful if you are using sort of negative shapes like I've used, that you are subtracting both in the numerator and the denominator. But besides that, there's really not too much to it. There's a table in the back of the book for kind of finding the centroids of various shapes. It kind of looks like this. This is also in the notes of the slides for the chapter. So if you don't have the book, you can look in the slides, but this is really handy for just knowing for like a triangle or for circles, squares, semicircles, whatever, what the centroid of those individual shapes are, so that you can then do composite shapes like this. So anyways, that's that. If you have any questions, as always, feel free to send me an email or message on Canvas, and I will be happy to respond and help out any way I can. Thanks.